welcome all of you to this first tutorial in the DGM course, Deep Generative Model course. Now, in this tutorials, now we shall be discussing predominantly on a simple MLP and how the forward pass will happen and how the back propagation using the error will happen. So, a couple of prerequisites that I'm assuming is that I'm assuming you guys know the basic structure of MLP, or the fully connected network that is there, and then I'm assuming that you are pretty much familiar with the task of regression. Okay, so wherein which it's a form of a supervised learning task in which you will be going to predict a number. Okay. Now these are a couple of prerequisites that I'm assuming that you know for this specific tutorial session. Okay. So I'll give a brief introduction about the supervised learning as a whole. See, in supervised learning, you know what is the right answer. Now, that is the underlying paradigm. So you have the data. That the data will be split into two parts. Now one is the training data. One is the training data. So this is the data now using which you try to understand the mapping between your input. Now the mapping between your input to your output. Okay. And supervised learning, you know the right answers. So you want to understand this mapping. So now let's call this mapping as function f. This is what you have learned. Now, how do you learn this? Now, this is learned using the training data. Now, how do you represent the training data? The data, training data, we represent it as D. So, when which you have pairs of xi, yi. So, when which xi is a feature and yi is your target label, and then you have m such x y pair. Okay? Xi is the input feature and yi is the target label given. Okay, target label. Okay, so depending on the size of the dimension, you can assume that x is in some real space, and y, since we are currently working under the assumption that we are going ahead with a regression task, you can assume that that is also in some real space. Okay. Now, what is the goal of this whole thing? Now, the overall goal is, so we want to minimize some error. Okay. That is the goal of the overall supervised learning. You want to minimize some error using the training data. Okay. And how does it look like? So you have a neural network. Okay. I'm preferably considering an MLP here. You'll be given the input xi, and then you will be predicting yi hat. Now xi is your input, and this yi hat which is there, now this is your prediction. Okay, this is your prediction. So we can represent this yi hat. You can represent this yi hat. So you use the function f on this data xi, and then you get the prediction. So now, how do you characterize the error? So the error or loss, what is called as now loss So you can say that this is some L, loss L, no, whichever, between your actual target label yi and the predicted label yi hat. Okay, this is the loss now which you want to minimize. Now this is the standard setting of your any supervised task. Now to understand this, so with a very simple intuition, now let's take a very nice example of football. Okay, now you have a football field, so in which you are training. Okay, this is a football field that you have, and so you're trying to do some kind of a penalty kick or something like that, or hockey or whatever. Okay, now this is your goal post. What happens is now you are training. This should be your actual trajectory. Now you should hit your ball here. This is your actual trajectory. But what is happening is now you are going off a bit. Okay, you're going off a bit, and then you are hitting till here. So now this deviation which is there, is actually the error. Now how do you, so the aim is now to reduce this error. Now how do you reduce this error? Now you go on looking into practicing it. Now go on trying it using the training data. Now I'm switching back to the context of supervised learning that we have in hand. So you go on practicing, and finally this error will reduce. Okay, this error will reduce. This will not become zero. This error that is there, now this error will reduce actually. Okay, good. So now given the input, you go ahead and predict the answer. This process is actually called as the forward pass. This is called as the forward pass. And then you go ahead and then from the outcome, you calculate the error and try to update things. And this is called as the backward pass, or famously called as back propagation. Now, how does this happen? That is the overall idea of so this is forward pass is from input to output. Now you have your input, and then it will convert it to output. And then in your backward pass or back propagation, what do? You calculate error. Okay. It's from error to weights. You update the weights. Each model is having some weights. You update it. Okay. So now for this is the brief introduction. Now what we shall do is, with this much of background in hand, we shall take a very simple neural network structure or an MLP structure. Okay, and then we will try to understand what are some of the intricacies that are there, and how does this backward propagation, back propagation, or the forward pass it actually happens. So let's try to look at both of them. Okay, so now for this purpose, what I shall do is I shall take my xi with two features. Now one is x1, the other is x2. My input has two features. Okay, or you can say that I, to represent that this is the ith example. You can have a subscript there. So now these are my input xi1 and xi2. Okay. Now normally what will happen is we have something called as input nodes. These are called as input nodes. So these are will not be having any weights per se. Now just the inputs will be given, and then you'll be having some hidden nodes. I'm taking two hidden nodes in this case. These are called as I'm having one hidden layer. You can have multiple hidden layers. Like you have one hidden layer, like that. You have multiple hidden layers like this. Okay. So and then here for a very simplistic approach, I'm just taking one hidden layer with two nodes. Okay, two hidden nodes in the hidden layer. Okay, and then I'll have a simple output node. Okay. So this is my output node. Okay, now this is the structure which is there. So now let's put in some weights. Now, this is a fully connected network or multi-layer perceptron. So there's both the inputs. Everything from the previous layer will be connecting to everything in the next layer. Now, that is the overall idea. Okay. Okay, this will be there. Then, so let's make it more colorful. And then finally, we will have an output. Here, output will be yi hat. Okay, good. So now, let's try to put some names to this. Now, we haven't done any namings for this. So now, this, I shall call that. I'll use the same coloring convention so that it is comfortable. Now this is A in the first layer, first node. This is A in the first layer, second node. Okay. So now all these nodes, I'm calling it as A. Okay. A is, this is, let's say this is IJ I have. Now this is the layer number. This is the node number. Okay. And similarly, for the remaining things also, this is A, second layer, first node. This is A, second layer, second node. And this will be A, third layer, first node. I have named each of those nodes. I'm using A just to specify that it is an activation. Okay. For that reason, I'm using the word A. So now let's try to put on the names for the weights. How do I represent? How do I name these weights? Okay. Now I use W as weight. W. Okay. Now from which node to which node it is connecting. Okay. Now you can say that from the first node, it is from the first node of the first layer, it is connecting to the first node of the second layer. Now what I shall do is I'll call this 1, 1, okay, of layer 1. So let's try to understand these indices. Now my notation will be W I comma j comma k. Now this k that is there, now this will be the which layer? I can call it as the previous layer. Now this I which is there, I call it as the destination node, and this j which is there, I call it as the source node. Okay. Because of which, so this will be, and this will be W. It is going to the second node from the first node of the first layer. Okay. And this will be W from the to the first node from the second node of the first layer. Now this will be to the second node from the second node of the first layer. Okay. And similarly for this, W So the layer will be 2. Okay. This will be from to the first node, from the first node. This will be to the first node from the second node. Now, similarly, you can extrapolate these things. Okay. I presume that these nomenclatures are pretty much clear. Now, these are the standard nomenclatures that are being used. Okay. So now, how do you compute these values of A's? Now I have these W. Oh, there will always be biases also. It will be there. Okay. Yeah, I'll do it when I go ahead with writing the activation functions. I'll name them. Okay. So now let's take how do I compute this A? 21. Is it A21? Yes. How is this A21 computed? Now for A21, that is this outcome, you have this and this. You have this xi1, which is the same as A11. Now since it's the input node, this value and this value will be same. This, the first feature, now it will be multiplied by its respective weight. Okay. Now we can use it xi1. The convention is first the weight will come W1, into xi1 plus W1, 2, 1 into xi2 plus I need some bias, right? Now I should be indicating that bias as well. Now, how do I indicate that bias? Now I'll give it the term B. Now I should be representing the node and other stuff, right? Now what I'll do is, now this is at layer 1, the first node. Okay, I shall be using the same convention. This is an additive bias that I shall be using. Now to this, now we need an activation function. Now let's say that I'm using the activation function G. So we all know that the couple of famous activation functions that we have are one is sigmoid activation function. Sigmoid, where in which the input is X. Okay, or okay, let's not confuse X. We have already used for input. Let's consider it as some Z. If Z is my input, it is 1 over 1 plus e to the power of minus Z. This is sigmoid. And then we have ReLU, rectified linear unit. Now here G of Z, now what will be the value? This will be 0 if Z is less than or equal to 0, or it will be Z if Z is greater than 0. Okay. Now, why do we use these activation functions? These activation functions are specifically used for smoothness, now to model more complex relations between input and output. Now, we normally use this activation function. Okay. Now, similarly, you have tanh, you have many such activation functions. Okay. We'll not be going in detail with that. Okay. So now, this is how you calculate this. Similarly, you calculate this. Okay. So now, normally, what do we do is this summation which is there. Now we normally call it as Z. Okay. Preferably use small z. Okay, fine, no problem. Z which is there. Now this Z, you want to name them the same indices of A. We use it. Okay. This is Z. This is one more representation that is needed for us going ahead. And similarly, let's compute for A22. So now A22 will be, so again, So you can use the same activation function, or you can use a different activation function, but people prefer to use the same activation function throughout. Okay, that is the overall idea. Now g of w from layer 1, you're connecting to the second layer from the first one, xi1 plus w22 from the first one into xi2 plus b12. Okay, this is the one. And then finally you want to compute the outcome. So now A13, how do you compute? This is W211 into A21. Okay, this into this outcome, this into this, plus this into this. Okay, plus W from the second layer 122 into A22, and then you need an additive value in the second layer, the first node, this, you pass it through an activation function. Now since this is the last node that we have, this is what we represent it as yi hat. Now this is our predicted value. Okay, this is our predicted value. Okay, now this is the overall process of forward propagation. Now this is, if you have multiple layers, accordingly you go ahead. So I presume that this is clear. Okay, so now then what do we do is, now here it is evident that this values are fixed. Now why are these fixed? Now these are nothing but input, so these are fixed. Okay, so now if you want to choose if you want to reduce the error, now these weights that are there, now all these weights are the ones that needs to be modulated. Okay, now this depends on this depends on this, which is internally depend on this. You cannot change this input, so you can only change the weights of it. Now similarly you can extrapolate it to everywhere. So now what do we do is, now all the parameters that are there, now we put it as a list. Okay, we call it as theta. Okay, so wherein which we put all the parameters. Okay, so all the parameters of the network that we have. Okay, because of which we represent yi hat equals the function f, which is having the parameters theta of xi. Okay, now this function can be anything. Now this function can be a linear regression, this function can be a polynomial regression, it can be a neural network. Now depending on what is your choice, now you go ahead. Okay, now this is the forward pass. Okay, this is the forward pass that we have. Okay, so now the next step, now once you have done the forward pass, the next step at hand is error computation. Okay, so now see, the idea is you need to reduce the error using the training data. Now that is pretty much clear for that. Okay, so now what is the error? It depends on the task that you are going ahead. Now if it is a classification task that you are going ahead, we normally use CCE laws. Now if you are going ahead with some reconstruction task, now that is what we shall be looking into in most of our generative cases. Now we'll be looking into the MSE laws or the reconstruction laws that we have. We have KL divergence. Okay, so on and so forth. We have a lot of loss functions, depending on the structure or what is the aim that we are trying to achieve. Okay. So now in this current case, now we shall take a very simple loss. Okay. Now I'll call this L. We will be using the mean squared error loss, yeah, famously called as MSE loss. Famously called as mean square error that we have. Now we shall be using this. Now, how do I have this? Now, this loss for one specific instance. Now we are only taking one data point. Now, if you are having multiple data points, you just accumulate and take out an average of the thing. Okay. Now for that specific instance that we have, 1 over 2 yi. Now yi is your actual target label minus whatever the prediction that you have got. Okay, if theta of x, or this is same as half into yi minus yi hat, your prediction also. This is our MSE laws, that is that. Okay, so now we want to reduce this specific MSE loss that we have in hand. Okay, so I presume that that is clear. So now I want to just, for completeness sake, so I want to reiterate that so we are assuming only one training point. If you have multiple training points, now what you will accumulate all the error, you take a sum of it, and then you divide it by number of points that you have considered, now which will give you the average of it. Okay. Now you're assuming one thing, and then the error that is there. This is what we want to minimize. Okay? This is the error that we want to minimize. Now, how do we minimize this? Okay. Standard trick that is known to all of us, that is, we minimize the function by computing its derivative with respect to what we can optimize. Okay. Now, you cannot modify or change. You cannot modify or change the input. The only thing that we can optimize is the parameters that are involved. So finally, so we want to minimize this by computing the derivatives with respect to the parameters. So we minimize any function by computing its derivatives with respect to what we can optimize or what we can change. Now this is famously written as a optimization function. I shall not be, I'm not assuming that, so you are familiar with the optimization. Okay, so I'll not be going ahead and writing any optimization equations. Okay, so now we can only modify theta. Now that too, I take a specific instance of it. Now let's take that. So we are taking a specific parameter wij k. That is at the kth layer. Okay, the previous layer is kth layer. The next layer is k plus 1 layer. Now from the jth node of the kth layer, I am connecting to the ith node of the k plus 1th layer. The weight is what I am considering. I have the loss L. Now I compute its gradient, dou L by dou. So I want to find this gradient. Once I find this gradient, I'll be using the gradient descent, which all of us are actually aware of. So then we perform gradient descent. Then we perform gradient descent. How does this gradient descent will work? The weight is updated via, you take the previous weight and then you use a learning rate into the gradient or the derivative that you have computed. Okay. Now this is the standard backpropagation that we do using gradient descent. Now, this alpha which is there, this is what is called as the learning rate. Now, this alpha that we have here, this is learning rate. We need a lot of knack in choosing this learning rate that we shall learn in our coming tutorials. So learning rate, this belongs to, so the positive R. Okay, this is positive real number. Okay, now we shall be going ahead with what we shall be doing is backpropagation. We shall be doing backpropagation with gradient descent. Okay, this is what we shall be doing. Okay, so now what does this derivative actually say? What is the intuitive idea behind this derivative? So now if you increase this uh, parameter that you have considered, okay, if you change this, now how does it affects the loss? Okay, now that is what we want to actually find it. Okay, so now if we increase or change, okay, we we increase this weight jk, how much does loss change? That is what we are looking at. That is rate of change of loss with respect to weight. Okay, so now what we shall do is, now to understand the backpropagation in much more detail, now let's take one specific weight uh, in mind. Okay, now let's consider the weight W1 1. Okay, now let's consider this weight. Let's consider this weight for understanding. Okay, so now what is that we want to find now? Now we want to see that how the loss will get affected as I change this weight. Okay, now in that, the first thing that we should need to do is, now we should know what is the path uh, this W11 is being involved. Now as you can see here, this is the path in which W11 is involved. Okay, now let's highlight that path. So just for okay, this is too dark, this is, it's okay, this is too light. What I shall do is, this is 2 mm. Okay, now this is the path in which now it is going. This is the first thing. Now first we should look at, now what is the path that is involved. Now let's handle this. Once we have the path from this weight under consideration to the output, then we can look at it. So now Now it is, I am assuming that all of you are again know the basic idea of chain rule here. This output which is there is affected by this value of A13. Okay. Now in this path, A13 is affected by this weight. Okay. And this weight is in the chain. And this. Okay. There is a chain that is happening that now we should be taking into consideration. Okay. Now let's write it down. How does it propagate? So the loss that is there is directly dependent on the output. Okay. Which is same as A31. Okay. This is the first step. Okay. So now the loss which is there is directly dependent on this A31. Okay. Now, how is this A31? Now, this A31 which I have is related to this. Okay. So now that means that I'll have delta A31 Z31. Correct? Now into now this Z31 now which is this value now which is there in the path. Okay. It is dependent on A21. Okay. A22 will not come in the path. That is this Z31 which is there. Now it is dependent on A21. Okay. And then the A21 which we have computed, this A21 is dependent on this Z21. And this Z21 is dependent on this W111. Okay. Now you should actually trace back the path. This is A21 which is there is dependent on this Z21 and this Z21 which is there is dependent on this weight W111. Okay. Now this is the full backpropagation calculation now using the chain rule now which we are able to do it. Now I have pre-computed all these values. I have just taken the same equations and written them again. And then what I have done is I have taken a very simple feature input now which is 1 and 0. Now this is your input, right? And I'm considering all weights and biases that I have is 1. And then if I go ahead with this computation, now A21, this will be the computation. Now your weight into this 1 plus weight into the 0, you get this value. Similarly, now I have computed my output. Okay. And this is my loss. So now let's go back to our loss gradient equation. Now let me copy this. I have written it in a very way. Copy this. Okay. And let me paste it here. This is the same equation. No. Okay. So now one thing that I can change here is this is nothing but yi hat. So what I can do is I can replace this. Okay. For all practical purposes, I can replace this with yi hat. Okay. So now let's go ahead and compute the gradients. The first thing that I want to compute is how the loss will change with respect to my yi hat. Okay. Now I just want to write the loss computation. L equals half into yi minus yi hat. Okay. If I take the derivative of this L with respect to this yi, now this will be, oh, there is a square here missing. Yeah. Now this will be yi minus yi hat. Okay. Now you can, this is like d by dx of x square is 2x. Okay. So you get 2 into this term, and this 2 and this 2 will get cancelled. So you get the term. Okay. I am assuming that you know all those basic rules of differential calculus. Yeah, I have computed this now. So now the next thing that I want to compute is, now how is my yi hat I have is dependent on this Z31. Okay. Just to give you a reminder, how does this yi hat is sigmoid of this Z31, correct? Now you should be taking the derivative here. Now it will be, the derivative will be sigmoid of 31 into 1 minus sigmoid of, this is same as yi hat into 1 minus yi hat. Okay. I have computed two terms now. This term has been computed, this term has been computed. So now let's take how my Z31 is dependent on A21. Okay. To understand that, first let us compute how is Z31 equals second layer from 1 to 1 A21 plus second layer from yeah, let me go there. Let's go back to equations and then compute. W into plus there is a bias term B, this is a term. So now when you compute, when you take the derivative of A21, okay, it will be the weight, this will be, okay. Now you have computed this term, and this term. How is this related now? So now you should be calculating A21. Now how is it dependent on Z21? Okay. Now what is this? A21 is sigmoid of Z21. That means that this will be, let's change the color, let's be uniform in terms of color. This is 21 into 1 minus, is the same as A21 into 1 minus A21. Okay. So now the next one, so this term we are done, this term we are done, this term we are done, this term we are done. How is this Z21 dependent on W11 is the next question. Okay. Now, how is the Z21 dependent on my W1, 1. Okay, this is my next question. Now, how does it happen? Now, let's compute it. Here, Z21 equals W11 into X I1 plus W121 into X I2 plus B11, okay, because of which this will be X I1. Okay, so now we have effectively calculated all of them. So now let's put all of them together into one equation. Thus, the laws this will be, let's calculate each of those, take each of the term. So yi minus yi hat, this is the first term. This term pertaining to this, okay, this. Okay, if we want, we can label it. This is 1, this is 2, this is 3, this is 4, this is 5. 1, 2, 3, 4, 5. Just need to multiply each of them. Okay. So this into the second term is yi hat into 1 minus yi hat into the third term as w1 comma 1 2 into a21 into 1 minus a21 into x. Okay, now this will be the gradient of the whole thing. Now you just need to compute this particular gradient. Now, similarly, once you have computed the gradient, then what do? You apply this updation method. So now, because of which your weight will get updated. Now this you do it for all the weights that are there in your whole set of theta. Now you do it, because of which your weight updation will happen. Okay. So now how does the overall training procedure look like? Now how does the overall training procedure look like? Now let's shed some light on it. Overall training procedure. So what we do is, rather than taking each example at a time, we take a batch of them. The overall data, now that we have m examples, now what do? You divide them into examples of b batches. Okay. So now let's take that I have a batch size of b, and then now you have m examples. In each batch you will have b examples. Now let's say that I have some k batches. Now my overall data now will be a set like d1 till dk. Okay. When with each bi, now we'll be having b examples. Now I'm assuming that m is perfectly divisible by b. Now if not, in the last batch there will be some small number of examples. Fine, no problem. So now what do we do is, now and then this is one, right? Now we want to decide on how many times you want to iterate over the whole data. Iterate over the whole data. Okay, that is called as epochs. Let's say that I have decided that I want to go ahead and iterate over the whole data max epoch times. Okay, I want to iterate over the whole data max epoch. Okay, so now Then what will happen is for E, I'm assuming that you know Python and I'm writing it in a Python way. Okay, E in range of max epoch. Okay, and then for di in D. Okay, you take one di. Now, each di will have a bunch of x's and y. Okay, now, all the x put together, I call it as capital X and capital Y, where which x is your input and y is your feature. Now, what do you do? Now, you calculate y hat, which is nothing but you take this function and then pass this x. Okay, you get this, and then you compute loss of y comma y hat. Okay, you compute this. This is what is called as the forward pass, and this is it is loss computation. Okay, and then the third step, I'll just write it in alphabets. The third step is you obtain the gradients. Obtain the gradients. Okay. Now, once you have obtained the gradients, so then what do? You update the weights. Okay. Now, this is the standard procedure that we shall be following in most of the cases. There will be some mix and match here and there, but overall structure remains the same. Now you'll be running over this whole data. Okay, this is one time you will run over the data. Now you finish off this k times. The k times this will happen. So the number of times in which the weights are updated, that is called as iteration. And how many number of times you want to iterate over the whole data, that is called as maximum epochs. Unless specified, this is the standard training procedure that is used. And then you use the test data to calculate the predictions. And then you measure it with whatever metric that you have in hand or have in as per the choice of the problem that you have. This is the overall idea of the training procedure, the forward pass. So, what did we discuss in today's tutorials? Today's tutorial was predominantly on the structure of simple MLP that we have considered. Okay. We considered the idea of mapping, okay, and then the idea of error, and then we took a very simple network into consideration, and then we understood the components that are there in this network and how do you put their names, and then we understood the forward pass, okay, and then how do you compute the error, and then we understood the idea of gradient descent, and how do you apply the chain rule in obtaining the gradients. And once you have, and then this is the forward pass with a simple example. And once you have that, now how do you compute the gradients? Each one of them we took separately, and then we computed the gradients, and then we computed the total gradient for one weight. And the same thing will be repeated for all the weights, and then you update it once. And then we looked at the overall training procedure of the supervised learning in most of the cases, unless specified. Now there will be some here and there, some small modifications will be there. Apart from that, the overall structure almost remains the same. Okay. Now this is what we have discussed today. Now thank you for patiently listening to me. In the next session, so we shall be in the next tutorials, we shall be looking into the PyTorch and then working with PyTorch. Thank you.